What is time? We measure it by Earth's rotation around the Sun. But what if there were a more universal way? What if we used the universe itself as a clock? From the perspective of any arbitrary system of mass, they observe a radial receding of other matter in the form of galaxies on the galactic scale. This receding takes place through time, and thus galaxies move further and further apart as time ticks on. Thus the entire universe can be perceived as a giant clock. Note that this receding occurs via Hubble's constant, h0. However, there is much dispute over the value of Hubble's constant. One theory is that Hubble's constant changes over time. Since we are interested in the fundamentals of time, we will want to take the most original value from the oldest measured light from the beginning of our universe, and thus we will use the low end of the cosmic microwave background calculations of 66 kilometers per second per megaparsec. Now I'm a very visual person, and I find it extremely useful to visualize mathematics in order to fully understand them. Here, we're going to use some cartoons to show how to track time with galaxy regression. Given any arbitrary observer in the universe with mass mcis, that observer will experience galaxies moving away at Hubble's constant. Now in reality, this regression is radial and in all directions, but for simplicity, we will use only a single arbitrary direction. Because information travels via light, distance and time for a given galaxy are related by the speed of light. When we receive light from galaxies regressing at Hubble's constant, the change in time and the change in distance from us are related by its average distance and Hubble's constant. This is because Hubble's constant regression rate changes linearly with distance. Now let's consider a radial spatial dimension of time, t prime, which has a positive value in both plus and minus x, y, or z dimensions. Thus, its magnitude is twice that of a directional spatial dimension in 3D space, and can be thought of as increasing entropy on the galactic scale by Hubble's constant. Thus, the sum of the change in time of information received from galaxies in equal and opposite directions in space is considered. Now, it turns out that we can greatly simplify our equations by setting the starting position of our regressing galaxies in both time and distance to 0. This allows us to completely remove the distance term and have our time dimension t prime in terms of simply 1 over Hubble's constant. Another useful conversion we are going to utilize is taking Hubble's constant and converting it from its distance per second units to an acceleration in terms of meters per second squared. This is done via the speed of light, via the time-distance equation that we introduced earlier, and gives us time as a spatial dimension equal to the speed of light divided by Hubble's constant as an acceleration term, which we will be denoting as h0 prime. Now that we have a definition of time as a radial spatial dimension of entropy change, if we look at other radially symmetric phenomena in our universe, we can identify space-time curvature of general relativity as also fitting into this radially symmetric category. This begs the question as to whether a relationship exists between these two phenomena. We're going to build on Einstein's elevator analogy, which demonstrates the equivalence between the force of gravity felt on Earth and that of an elevator in space accelerating with the same force. This led to the idea of space-time curvature. Let's take this scenario to the next level. Imagine in our space elevator we have a fabric with 2 bowling balls, which create a curvature in the fabric when the elevator accelerates. The equal and opposite force from the elevator is being translated into a physical curvature of the fabric. We can assign a force to this curvature and call it the curvature force Fc. Now the result of this curvature should be a seemingly attractive force between the bowling balls as they attempt to minimize the curvature of the fabric, this force being analogous to that of the gravitational force, driven by minimizing space-time curvature between all objects of mass. So what is the analogous force to the accelerating elevator that is creating space-time curvature? Well, you may have guessed it. Let's take our 2 objects of mass attracting each other gravitationally and put them in a hypothetical box. Now let's assume that the space-time curvature radially around them is due to the box accelerating through some dimension, with a force equal and opposite to the space-time curvature force. which we will apply Newton's law to, giving us an equation relating this force to the mass of the system and an acceleration term, the acceleration of curvature, AC. Right now we won't bother with the plus-minus directionalities as it's not yet relevant. Now let's construct a model where our system's curvature force is being generated by a gravitational attraction from another mass, mc, through a distance r in this yet-to-be-identified dimension. Using this model, we can generate a gravitational force equation, which when combined with our Newton's law equation, and canceling out the mass of the system, gives us a third equation with three variables where we can identify the mass of this gravitationally attractive system by identifying its acceleration and distance relative to our system through this unidentified dimension. Interestingly, when we plug in the radius of our universe for the distance term of 46.5 billion light years converted to meters, and 2 times Hubble's constant as the acceleration term in meters per second squared, representing the acceleration of the radial spatial dimension of time that we discussed earlier, the result is a mass representing all of the relativistic energy in the universe. Consider that our arbitrary system of mass can be represented by all relativistic energy in the universe. This implies that all relativistic energy, aka space-time curvature, is due to our universe orbiting itself through the radially symmetric time dimension we introduced earlier. This creating a model for cyclical time where opposite energy poles exist across the orbit, with centers of mass separated by the distance to the cosmological horizon. Returning to our space-time curvature equation, if we use Hubble's constant prime without doubling as the acceleration term, and we use the Hubble's horizon derived from the same CMB constant that we used earlier, we get a mass representing about 5% of the total relativistic energy mass of the universe, which is representative of the total baryonic matter in the universe. Both of our calculated mass terms are consistent with literature values, the equations of which can be easily derived using our radial time dimension equations derived in this presentation. Let's take a look at our baryon mass orbit. It appears to reflect that of causal connectivity, since we cannot gain information past the Hubble horizon due to the speed of light in Hubble's constant. This orbit, like the energy orbit, also takes place through time, but consists of less directional microstate variability, a concept we will cover in detail in a different presentation. Also note, for visualization purposes, what it means for these orbits to take place in a radial time dimension is that this orbit occurs in all directions from the observer, such that all points on the cosmic and Hubble horizon surfaces are at the opposite energy poles of these orbits, which in essence is a cosmic scale quantum orbital with energy levels reminiscent of an atom. I decided to denote these two sections of our universe as space-time and time-space. Note that space-time and time-space overlap within the causally connected portion of our universe, with time-space extending beyond what we can observe. In another presentation, I will discuss how the interactions between the causally disconnected portion of time-space is responsible for dark energy. If you're interested in reading more of my work, look up my paper on Vixra, The Geometry of Space and Time by Ben Lassell. The link will be below. Until then, I greatly appreciated your attention and hope you found this interesting and insightful. If you liked my content, I plan to do much more of this, and I would greatly appreciate a like on the video, a subscription to my channel, and or a comment or question in the comment section, and I'll do my best to get to all of them. I plan to roll out much more content in the future, and we're going to dive deep. Till next time, much love.